Okay, I guess we're going to get started. This is the beginning of the application session. There's four of us who are going to be talking. I'm Nelson Morgan. I'm from the International Computer Science Institute, which is a nonprofit that's closely affiliated to campus, but I'm also with the ECS. I'm going to be representing a lot of work that a lot of people did, a bunch of people from our institute and a bunch of students from ECS, not so much what I did. So the application that I'm going to talk about first is what we call the meeting application. This is for what I'd call real meetings. And by real meetings, I mean meetings that were not artificially designed in order to fulfill some scientific goal. Meetings that people were going to have anyway. And you find in general that people take pretty inconsistent notes. I myself take pretty lousy notes. And so you'd like to have the words, certainly, that were uttered, but you'd also like to know who was speaking them, and maybe you'd like to find out some other things, like who was dominating the conversation, what were the action items that came out of the meeting, what was the agenda after all. You may have had some idea of an agenda going in, but may not have lasted too long. You might want information that is covering more than one meeting. So tracking things between different meetings. And in general, you might want to be able to extract information from previous meetings or from the meeting that you're in right now. In general, want to search for it. This is a picture of one such meeting diarizer, or meeting diarist, that was done as part of a European project. There's a section here where it shows who is speaking when, a section here that has what the words presumably are, and then various other pieces of information that you try to pull out of the meeting. So there's a number of challenges to this. First is that most meeting rooms are not very heavily instrumented. There are some experimental meeting rooms where you have a huge microphone array and you can kind of beam in on who is speaking. But in general, you don't have that when people are getting together and talking about stuff they want to do. Consequently, you end up with a bunch of noise and reverberation from the bounces of the acoustic waves off the walls. And the signal is a little messed up, and this tends to screw up speech recognizers. The other thing is that you do care about the speed. For many applications, you want real time. And in fact, for some applications, you need better than real time. You can imagine that if you had 1,000 hours of speech you were trying to go through to get some information, you wouldn't want to have to wait 1,000 hours to get it done. So we do care about speed, but we care about this not just for the speech recognition part, because the full meeting application requires also information about who's speaking when. And the other thing is you care about more than speed. You actually care about improving the accuracy of what you're doing. Again, in many real situations, you're going to have pretty poor signal, and the speech recognition in current systems tends to do badly. So this raises a few primary questions that we're approaching in this. First is kind of the obvious one: can the entire application be parallelized? Can we use the methods you've been hearing about to parallelize them? Secondly, can that actually help accuracy? Not just make it faster, but can it make it better? And the third thing is, can new approaches to this be coded by mere mortals, by someone who's not a heroic or expert programmer? A bunch of us are not that, and we're doing work in extending the scientific research. And so can we actually make new things, still be efficient and easily coded? So here's a block diagram of the overall application. You have the speech recognition, which produces what was said. You have what's called speaker diarization, which produces who spoke when. Then you put them together and you said who said what. And then there's these other modules like indexing and searching and retrieval and so forth. And you're not really going to know whether you have efficiently parallelized the entire application until you do all of these things. You can't just do the speech recognition. But let's focus on the speech recognition for a minute. This is how all modern speech recognizers look. First, they do some signal processing on the speech, and by speech I actually mean, of course, the electrical signal coming from the microphone, or amplified. And then this is measured, whatever the signal processing variables are, they're measured around 100 times a second, and 100 times a second you get some estimate of how probable it is that those observed features came from there being a particular speech sound. And the way you get those probabilities is from some acoustic parameters in a statistical model that you've previously trained, typically on a whole bunch of data. Then those little probabilities, by little, I don't mean size, I mean probabilities corresponding to, say, 10 milliseconds, you string a whole bunch of them together and try to figure out what was said. And you also make use of prior probabilities that you have of how likely it is, for instance, that a particular word follows the previous 3 words. And then there's a bridge between the individual speech sounds and the words, and those are the pronunciations. So that's how all speech recognizers look, suppressing a lot of detail, obviously. Now, at a high level, this is the system level pattern is pipe and filter with task parallelism. Most systems do integrate the local probability estimate with the decoder. It's sort of all one thing. And if you look at how much time each is taking on a single processor, all of this stuff really dominates. And the signal processing stream computing these features is actually a small part. The question is, should it be, if we actually want to improve performance? So we're kind of banking on the idea that, no, it should actually be grown quite a bit. And we call this going from one stream to multi-streams and to many streams, which you can easily imagine going to multi-core and many-core. Okay, so as I was saying before, under good conditions, you actually do okay. You get something like 90% or more accuracy. This is usually stated in terms of the other side of what's the word error rate. But under many conditions, if the microphone is not right here, you actually have quite a bit worse. You get maybe a third of the words wrong or more. So people have found over the last number of years that, in fact, having several different signal processing methods, not just a single one, looking at the speech signal in different ways, actually helps. So an open question is whether or not a huge number of streams can, in fact, provide greater robustness to noise and reverberation and other degradations. And I should say that a lot of this kind of perspective comes from analysis of data people have collected in small mammals in their primary auditory cortex. And they found, in fact, that there's a whole range of representations. It's not just a single nice one, a single good kind of spectrum or something. So we've done a bunch of work on this, and we, in fact, find with up to 28 streams anyway that we get a really nice improvement. We can get rid of, on a pretty difficult task, getting rid of almost half of the errors. So that's good. And then the picture I showed before gets changed in just this simple way. Instead of having one signal processing method, you have lots of them. Now, the decoder has less to do with improving the accuracy. There are very good methods for decoding or searching through the information that you have to find the most likely string of words. But it's tricky to parallelize. And so people in the parallel lab have paid a lot of attention to that. So this outputs the most likely word sequence or a graph of some kind that shows a range of possible word sequences given the input data. One of the current implementations being done in the Parallab is it's implemented as a weighted finite state transducer. It's basically a great big graph, and you have to traverse it. And that's the tricky part, because it's not just dense linear algebra. There is, however, dense linear algebra also. There's a set of states and arcs, and the innermost loop can be is updating these nodes, and it can be parallel over the states or the arcs, and it's typically formulated as a SIMD, and in fact this was implemented with CUDA on an NVIDIA card. So these different parts of the recognizer break out like this. The explicitly parallel part is these multiple feature streams. You basically can run each of them on a different core. You also can parallelize even further because a lot of the parts, the signal processing components, which I won't go into in detail unless you ask me, are pretty much dense linear algebra easily implemented SIMD, and so forth. The tricky stuff, as I said, is the decoder, and it's more than dense linear algebra. It's the graph traversal. And what we found was that for the compute-intensive part, we got an 18 times speed up on the NVIDIA card, and 4 times for the communication part. Overall, the number came to 11 times. So G.K. Chung was the one who was leading that effort. He's a student of Kurt Kreutzer's and did a great job. As I said, it's not just speech recognition. It's also this part called diarization. And diarization consists of segmentation of the speech signal into regions that you think are breakpoints between different speakers. And then a clustering where you cluster, oh, this part is in some way quite similar to that part, so we'll call them both speaker A, and so on. Once you do that, you go back and do segmentation again, then you do clustering again. So it's an iterative process because there isn't an explicit solution to it. So this estimates who spoke when. It can do it without knowledge of how many speakers there are or any kind of models that you start with for the speakers, although it's great if you have them. You also don't, for this general process, you don't need the words. You don't need what language is spoken. In the case of the meeting diarist, you will have both of those because if you didn't know what language was spoken, you'd have trouble doing the recognition. Most of this is pretty straightforward to parallelize, but it has a dynamic programming component, which also is a kind of graph traversal. You can end up with, this is a lovely picture here. Basically, you can pick out particular people and say, oh, I only want the part that's being spoken by Roz Bodick, or maybe I only want to hear the laughter. You can also put in a word and say, I just want to find segments where they're talking about cash. Here's a little part that's showing another way in which we can actually get more accuracy. Yeah?
Sorry, quick question on
sure.
cache. You have to look for places where cache as in cache memory as opposed to when you're looking for CACHE, you're looking for cache as in cache memory and not people talking about who's going to pay for lunch.
Right. So what you hope is that, so those kind of homonym distinctions, you really, for the most part, can't tell from the acoustics, but you can tell from the language model. So it could be, if the language model is good, it will give you the right text set of words out, and then this search will find it. But in fact, there are spoken term detection things where people worry about the sounds. They might give you both, for instance. In this case, it would only give you the one. Good question. Okay, so it's not only the speech recognition that can be improved, actually in accuracy by putting more flops on it. You actually can improve the diarization as well. Now this graph shows diarization error rate. This is basically the percentage of time that you're wrong about who was speaking when. And this is number of cores that are dedicated to an offline system for an online diarization. So what that means is that the online diarization, you're attempting to figure out who's speaking when as you go along. In offline, you have the whole, say, a whole file of people speaking. And so you can generally do much better with offline. But there are many applications where you need to do something with online. And there's a kind of hybrid of the two where you can be doing offline on everything that you've seen so far, but that takes a lot more computation. And as you throw more computation at it, in fact, this error rate does go down. So that's a pretty direct way we can get this improvement. So in summary, a few things. The goal of people working on the meeting diarist, myself, I'm a speech researcher. My goal is to improve the application performance. So for me, parallelization is really only a means towards that end. And aside from making the meeting diarist itself work well, we want to speed up the research process. We want to speed up the training time, which I didn't really talk about for these models. Real time or faster, even faster than real time can actually be useful in practice. Each of these components needs to be parallelized. If you're interested in the whole application, you have Amdahl's law implications if you only parallelize the part that's obvious. The components do in fact fit into known structural and computational patterns, so that's handy. There's significant speedups that have been achieved on the speech recognizer, and the diarization is an additional component, and we get not only speedups, but we actually get error reductions from what we've been doing. And I believe that's it. Thank you. Any questions? Yes, sir.
So when you use more cores,
Just a second, he's got a mic coming.
thank you. So when you use more GPUs, do you pick a different model the more cores you have, or you just do more iterations, or is it something else?
So for the diarization graph I was
Yeah.
showing, what you do is you are able to look at more of the signal at once. So you can break it up in more pieces and so forth. So it allows the offline part to have a bigger and bigger role.
I see. So more history, sort of.
Yeah.
I see. Thanks.
Okay. So next talk is from Dave Wessel, who's done these great music applications.